Idea being that we've seen unit vectors before, and we could also think of u as being equal to cosine theta sine theta. Not really sure why I chose to write it there as opposed to below. I guess it doesn't really matter, but what's happening is you're taking really the dot product between the partial derivative vector and the unit vector. So just kind of off on the side here, I'll show you. If you have a vector containing your partial derivatives and you dot that against u, that would be the same as dotting it against cosine theta sine theta. All right, so that first line, that directional derivative, d sub u, is really what you would get if you just did the straight multiplication, leaving it in terms of u, all right, because u is u sub 1, u sub 2. If you dot it, that's what you would get as a result. But you could also get an alternative form, which I think is a more useful form, that involves the angle. Now, you don't always know the angle, but when you do, it's very meaningful. So we would say partial with respect to x cosine theta plus partial with respect to y cosine theta, sine theta. All right, so at this point, we're just focusing on skills. So what we want to do is find the directional derivative of each function when you have a given angle of theta. All right, so I have a coordinate, I have a function. So I'm going to find the partials. Partial with respect to x is just 2x. Partial with respect to y is just 2y. But I also need it at the particular coordinate. All right. When you're subbing in values, remember it's only the relevant values that you plug in. There's an x value and a y value. All right. So if I plug in the x value here, I'm going to get a 4. And if I plug in the y value here, I'm going to get a 2. All right, so my directional derivative, d sub u, in the direction of unit vector u, of function f at coordinates 2, 1, would be equal to, we could say 4u sub 1 plus 2u sub 2, but we have an angle. So this would expand to 4 cosine theta plus 2 sine theta, which in turn would become 4 cosine, because they told us the particular angle is pi over 4, plus 2 sine of pi over 4. All right, so the cosine of, yeah, so square root of 2 over 2 in each case. Ready to rock and roll. So 2 root 2 plus root 2 is going to be equal to 3 root 2. All right, so this is what we're calling the directional derivative at the coordinate where x is equal to 2, y is equal to 1. There's a z associated with that. You can figure it out. It's just 5. So if you're looking in 3 space, it would be the coordinates 2, 1, 5. Going off at an angle of pi over 4 from that direction, you would have a magnitude of 3 radical 2. So that rate of change would have a magnitude of 3 radical 2. All right, so that's what a directional derivative is telling us, is that you have a vector going off from that coordinate or those coordinates at a particular angle. This is what the magnitude of that vector would be. All right. So the rate of change, instantaneous rate of change if you want, thinking back to Calc 1. All right. So the second example follows the same suit. It's nothing more challenging, so I'll just pop a star on that one. All right, so it is the same general idea as the last question. Partial derivatives, substitute, and then we apply the definition, which is really just us saying, weird.
It's right on top.
No, I'm just noticing that.
Oh.
I wrote U sub 1 last time when it should have been a U sub 2. That's strange. Not for me. I mean, it's typical for me. It's just a strange occurrence. So we're looking at 4 U sub 1 plus 8 U sub 2, all right, which corresponds to cosine theta, sine theta, because we're talking about a unit vector, and unit vectors can have direction. So we're saying 4 cosine theta plus 8 sine theta. So 4 cosine pi over 4 plus 8 times the sine of pi over 4. And that's going to be equal to 4 times
square root of 2.
Over 2. 8 times the square root of 2 over 2. So 2 rad 2 plus 4 rad 2 will give us 6 rad 2. So then we get the gradient vector. Now the gradient vector is really not any more challenging. The good thing about this is really you're just looking at a more generalized version of a directional derivative, because you're talking about the partial derivatives just written in vector form. So not particular values, but general forms. Okay, so there's a blurb here. In most cases, there's one direction u where the directional derivative is the largest. This is the uphill direction. All right, but if you're at the top of the mountain, then that might not be true. You know, so you're thinking of surfaces. If you're at the top of the mountain, there would be no uphill from there. The only place you can go is downhill. So what happens is you end up with little micro movements from point to point as you move along a surface. So the gradient tells you the movement that involves the maximum rate of change, so the maximum slope. Right? So if you're trying to, let's say, climb a mountain and you want to have the most direct path there, you might say, well, I'll just go that way. But if there's a lot of twists and turns along the way, that could be a problem. Right? What the gradient does is it gives you a sense of what direction you should go in order to maximize your productivity, basically. Right? So the slope should be the greatest in order to have the most movement. Right? So, but the thing is, it's not always going to be true for all cases. So if the surface is not constant, then you can't assume that the rate of change is going to be the same for the whole trip. So maybe you take one step, and then you have to do a course correction. Then you take another step, and you have to do another course correction. So it can be kind of tedious and troublesome, but what the gradient really requires you to do is make a determination of the best path to take on a micro level, then start following that path for a smidge, then recompute the gradient at that new location to give you the new direction that you should follow. Follow that path for a smidge, and then recompute, and then follow that path for a smidge, and so on. So you might have these little micro paths that you're taking. Ultimately, it gives you the path of steepest ascent, gets you to the top of the mountain, but it doesn't seem like it's an effective way to do it, especially if you're stopping every 2 steps to whip out your calculator and figure out what the best path to take is. When in reality, you're like, that looks steeper than that, so I'm just going to climb that, you know. So common sense kind of kicks in, but the idea is that there is a mathematical approach that can be followed, right? And so that's where this comes into play. Right? So that's what all of this is saying. How do you find the gradient? Well, you find, well, this looks familiar, your partials. So upside down triangle. Yeah, there's a name for it.
That's what it's called.
It's called an upside down triangle. I believe NAMBLA?
It's upside down triangle.
Yeah, we're going with upside down triangle because I saw that South Park episode.
Oh my god.
So
That's funny.
Wait, which one?
It had to do with the food pyramid.
Skip the algorithm. Oh, yeah. I remember that one.
There you go. That's so stupid.
so yeah, that's how we're gonna do it. But again, if you look at what we're doing here, it's really just partial with respect to x, partial with respect to y. Put it all together, and you have your gradient. So 2x plus 2y.
Del.
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 Yeah, for short.
Del.
Yeah, it was nice.
Oh, that's it?
Yeah.
So what happens when we take the second gradient? What if we take the gradient of the possible
2i plus 2j.
This is just del.
It doesn't have the same meaning. Right now, we could find, it's not asking for it, but we could find the magnitude of this.
is just going to be
Because it is a vector.
it's just going to be 2 times x squared of x squared plus y squared.
All right, so, I mean, if you really want to get fancy, you can go back and substitute it in terms of the original function. You could say 2 root z, but that's not really necessary. But and again, this is not really asking for this, but there is a consequence of the, it's written here, maximum rate of change of the function f at AB. If you have the magnitude of your gradient, it occurs in the direction of the gradient. Right? So whatever the direction is, the directional derivative at this point, or whatever coordinate, its maximum rate of change will occur with this value in whatever that direction is. All right? So all of these properties come into play, so it's a nice little feature related to the gradient. The minimum rate of change occurs in the direction opposite of the gradient. And then you have some things related to orthogonality, but we'll get to that down the line. So, tackle a problem. Number 2 is pretty much the same thing. For number 3, it's saying, is there a direction u in which the rate of change of the temperature function given at is, and then give reasons for your answers. Jeez. So, function of 3 variables, so that's something to keep in mind. I need my partials. So we're looking at 2y, just 2y, right?
Yeah.
and then 2y, or I'm sorry, t partial with respect to x at the coordinate 1, -1, 1 would be equal to -2. Partial with respect to y would be 2x minus z. So 2 minus 1, I believe, is 1. And then partial with respect to z. That's just going to be a negative y, right? All right, so what it'll do is it'll come up with the gradient vector, just because we covered that, might as well. It's got 3 components. So 2y I plus 2x minus z j and then plus yk, so I'll just say minus yk. Now the magnitude of this could be complicated if I were to actually do it in algebraic form, but since I have it at a particular coordinate, I can figure out the gradient at that location. And we've already figured out these numbers. -2, 1, 1. So plus k. Then I would want the magnitude. So it looks like √6. Square root of 6, what's that approximately? Root 2.7?
No, I said 2 point something.
2 point something.
I would assume.
I would assume also. Does anybody have something other than 7? 2.45. All right, so we just figured out 2 things, one directly and one indirectly. We figured out, well, they were asking, is there a direction in which the rate of change of the temperature at this location is -3? So could I go off in a particular direction and have a rate of change be -3 degrees Celsius per meter, all right? And what we got here was the gradient value at 1, -1, 1, right? What this gives is the maximum rate of change. At 1, -1, 1. So if I were to take off at any direction from 1, -1, 1, the most rate of change that I could accomplish would be 2.45 degrees Celsius per meter. All right, I didn't include the units. But one of the properties tells us that the opposite of that would be the minimum rate of change. The negative magnitude of the gradient is the minimum rate of change. So what it's telling us is that no matter what direction I go off in from the coordinates 1, -1, 1, following the surface, I can achieve a maximum rate of change that is no greater than 2.45 and a minimum rate of change that is no less than negative 2.45. Right? Everything has to be in between. All right, so what we created were constraints. And so therefore, cannot reach 3 degrees Celsius per meter. Negative?
Yeah.
Negative. All right, well, or positive, doesn't matter. But the question was asking negative, and so it is true that we could not ever get to a -3 measure because the lowest we could ever get to is negative 2.45. All right. So the next one, I'm going to put a star on that because that just expands it to three variables, which we really just did. This was the prelude to the rule, and 4 is just an extension of that. So that should be fine. Temperature T at point x, y, z in a solid is given by that function. Find the direction from the point 2, 0, 50 in which the temperature increases most rapidly. All right, so we're looking for a gradient. So we need partials. So this will be fun. Now, it's actually not that bad, even though it's a very nightmarish looking original function. It's just, well, the 85 is constant, and when I'm taking the partial with respect to x, I'm treating 1 minus z over 100 as a constant multiple. So that's going to stay put. I don't have to do anything with that. All right, so I'm really just taking the derivative of the e to the negative x squared plus y squared. Now, this part, I'm going to think of it, or at least, well, in this case, I'm going to write it, but under normal circumstances, I'll think of it as negative x squared minus y squared, just to make the partial component a little easier. All right, so e to the negative, I'll still write it in its original form, multiplied by the derivative of the exponent with respect to x. All right, so we're looking at negative 2x. All right. Then what I want is the partial with respect to y. So same deal. Except multiplied by negative 2y. And then partial with respect to z. Now in this case, since I'm looking at a factor that contains everything except for a z, the e to the negative x squared plus y squared, that's what's going to be treated as a constant multiple. It's the other part that I would need to differentiate. Right, so I'm going to write this as e to the negative x squared plus y squared, and then I have to take the derivative of the other part. All right, the 85 is still constant, so that's still going to go away. All right, the derivative of 1 minus z over 100, well, that's 1 minus 1/100th, 1/100th z, so that's just going to be negative 1/100th. All right, so we have all our partials. Now we just have to evaluate it all. All right, because it says from the point 2, 0, 50. All right, so I could write the gradient vector if I wanted to, but I mean, it's a matter of just writing all of this I plus all of this j plus all of this k. That sounds like fun. Only to substitute in after the fact. So why not just substitute in first and then go from there? All right, so partial with respect to x. This is happening for 2, 0, 50. We got to do the same thing for partial with respect to y. and partial with respect to z. The good news is there's a lot of consistency from partial to partial because they all have the e to the negative x squared plus y squared in it. So you figured it out once, you figured it out for all three cases. Right? So the x and y values are 2 and 0. So if I plug in there,
So it's going to be -4.
that's going to be -4. Yeah, so e to the -4th power in each case. So for the first two situations, we're looking at 1 minus 50 over 100. So 1 minus a half is a half. E to the -4th. And that's true for both partial with respect to y.
Times
I'm
-4.
I'm getting there.
Sorry.
That's all right. All right.
For negative y, just zero out.
Say it again.
Wouldn't it just zero out, don't even touch it, really?
Yeah, the whole thing.
Because it has the y at the other side.
The
Right.
partial with y.
Okay.
So -2 times 2, -2 times 0, and then we have the e to the -4th multiplied by -1 over 100. All right, so we're looking at -2 e to the -4th, 0, and negative e to the -4th over 100. Now we can clean it up a little bit by making the negative exponents positive if we want, but I don't really see any benefit to that. All right, so what I want to do is make this gradient a, find the direction from, oh, it's just asking for a direction, so that's all we need. So -2 e to the -4th, 0, negative e to the -4th over 100. Okay. Now, if it asks for the magnitude, that would be a different story. It's saying what direction should we go in for the greatest temperature increase. That would be the direction. All right, it doesn't seem like a very clean direction, but it's a direction. If I wanted to know what the magnitude would be in that direction, I could figure that out also, but it's not calling for that. Because Calc 1 is, it might be like a fond, distant memory at this point. Where it's like, oh, I miss the days of Calc 1 when everything made sense and it was all, yeah. It's like, this is great. And then Calc 2 happened. And then, and here we are, you know. So, what's that? Generally, I like to think it does, but
I think it uses the look.
that could be fun.
It was harder to grasp.
Definitely.
This is just like Calc 2 and 3-dimensional stuff.
Exactly. And I think, in all honesty, I think the hardest part about this stuff is visualizing what it is you're supposed to be looking for.
Yeah.
You know, because if you don't know what the equation -x squared minus y squared plus 2x plus 6y minus 11 looks like in 3-space, it's like, you know, going back to Calc 1, I had an idea going into every problem whether there was going to be a relative max, relative min, point of inflection, what kind of concavity I was looking at, and all that good stuff, just because I could pop it in my calculator. If that's assuming I didn't know what the function looked like to begin with. If I didn't know, I would just pop it into my calculator, take a quick look, and say, okay, this is what I'm up against. Now I just got to make the math work itself out. Here it's a different story because you may not have a good visual sense of what is going on here. Right?
We'll
So,
our calculator in 3D.
or, yeah. So, anyway, these properties and rules come in probably more handy than you would expect. Right, just because of that idea. Right, so we call FAB a local maximum if there's an open disk R centered at a point AB, for which that f of AB is greater than or equal to f of x sub y, x comma y. What that means is that you have a particular point that's higher or equal to every other point on the surface, right? Or at least on that interval, right? Same idea for a local minimum, right? Both are called local extrema. Critical points, remember those from Calc 1. The point is a critical point. If AB is in the domain of F, it's very important. I mean, it's kind of stupid, but like, yeah, it would have to be within the domain in order to be a critical point. If that goes back to continuity, implies differentiability. So if you don't have a continuous point, if a point doesn't exist, yeah, the derivative may be equal to 0, but if there's no point there to begin with, then you're not really getting anything meaningful out of it, right? So what we get from this is the partial with respect to x has to be equal to the partial with respect to y, which has to be in turn equal to 0. Or one or both of them, one or both of the partials do not exist at that point, all right? So the point itself has to exist, but the partials don't have to exist, all right? So you plug in a, b to your original function and you get undefined, all bets are off. You're not looking for a critical value. You get something that exists, you take your partial with respect to x, partial with respect to y, plug those numbers in. If you get both of them to be equal to 0, or either of them to be non-existent, then you're looking at a critical value. All right, and we know from Calc 1 that critical values lead to local extrema. All right, there are starting points for determining whether there is an extreme value. Condition for local extrema: if f of xy has a local extremum at AB, then AB must be a critical point of that. All right, so that's what I just said. All right, now saddle points, that's new. So you get a whole blurb here. It's a saddle point if you have a critical value, critical point, and well, other things. So if every open disk centered, I really have to explain at some point what these open disks mean, but it really is just the idea that you're not talking about a particular interval. You know, in Calc 1, it was like on the interval A to B, you can go from 2 to 3. But in 3 space, you can go that distance in every possible direction. And so what it does is it creates a circular region. All right. So that's really what that's getting at. But I'll illustrate that at some point down the line. All right. Centered A and B contains points x, y in the domain for f, for which f of x, y is less than f of AB, and points x, y in the domain of f, for which f of x, y is greater than AB. All right. What does that mean? It means it's neither a maximum nor a minimum. All right. It means that there are points above it and there are points below it. It kind of has the same sort of feel as an inflection point, but in 3 space, right? It doesn't necessarily mean a transition of concavity, but it's along those lines where you'd have a critical value, you'd test it, maybe you do a sign chart, and then you'd say, oh, well, that critical value is not a local max or a local min because there's no sign change around it. So what is it? Well, maybe it's an inflection point, so you take the second derivative and go that route. All right, so this is the case of you got a critical value, you tested to see if it was a local max or min, it turned out it wasn't one of those. So what is it? We call it a saddle point. All right. So how do we find these things? Well, sometimes it's just a matter of doing a little bit of algebra. So critical points for the function. So first off, I would test for continuity. The test is not something formal that you need to do. You just look at it. Is there any bad value of x or y? No, that's perfectly fine. So we can get into our partials. So partial f with respect to x, it's going to be 2x plus 2. Partial, poor quality partial f with respect to y. Oh, sorry, it was negative 2x plus 2. Negative 2y plus 6. All right. So again, just going back to the definitions, if you have a point for which the partials are equal to 0, that would give us a critical value. If you have a point for which the partials do not exist, then you would also have potentially a critical value. So what I can do is set each of these equal to 0, classic Calc 1 maneuver. When in doubt, set it equal to 0 and solve. All right, so I got an A and a B value. All right, so we're looking for relative extremum at 1, 3, f of 1, 3. Figure that out in a second. I'm putting a question mark there because we don't know for sure. That's the investigate part. All right, now, based on the picture, it looks like maybe there's something there. We could plug in the 1, 3 for x and y. I'll just kind of do it right above the equation. -1 minus 9 plus 2 plus 18 minus 11. So -1? No, that's not right, is it? 7, 9, 0. Is it? Is it? It is negative. Oh, look at that. All right, so if this is going to be a relative extremum, then this would have to be the largest number. Based on that diagram, we know it would be a maximum. Right? There's more to it than that because you can't just rely on the picture. But for now, I mean, we have the picture, we might as well take advantage of it. If this is the largest value available, not only do we have a relative max, but we also have an absolute max. All right? So what can we do? Well, we can do a couple of things. One thing would actually be to try to get this into some other form. So f of x, y, again, I'm going to rewrite the whole thing. I'm looking at something that is definitely a quadric surface. Right? What that means is that it's a conic section that's just projected into 3 space. So it has the look of, you know, when you see x squared, y squared, you're thinking ellipse or hyperbola, maybe a sideways parabola, but they're both squared, so it wouldn't be that. Right? It could be any one of those figures. So a good strategy would be to use completing the square to get it into a standard form.
Does it matter if it's relatively extremum or extremum?
In this case, because there's only one, it would be an extremum.
Oh, okay.
Yeah, but I mean, if you use extrema instead of extremum, nobody's taking off points for that. I shouldn't say that. I'm sure there are many people who would take off points for that. I'm just not one of them. No, even there, I don't even think so. Everybody. No, B plus, sorry, and an A. All right, so we would complete the square here. So I am going to cut the B value in half, square it, and then divide by the leading coefficient. So it's going to be a -1.
Did you start recording?
I did. A good question.
Did you record last session?
The one I wasn't here for?
Yeah.
No.
So the mic's still
That being said, I just gotta sit down and do it. But I have the video from last semester. I'll post it up so that you at least have it. So anyway, I'm subtracting 1 here. You can't just subtract 1 from an expression and just say, oh, I wanted to do that. If that's the case, why not just add an x squared, subtract a 2x, add a y squared, subtract a 6y, and add an 11 and call it a day? You know, you can make it all 0. You know, if you're going to break math rules, break them like with authority. So, yeah, I got to correct for that. So I'm subtracting an arbitrary 1 here. Arbitrary. It's coming from the completing the square process. But I have to correct for that by adding a 1. Same idea here. I have to subtract a 9 because the b value cut it in half becomes 3. Squared is 9. Divided by the leading coefficient is -9. But then I have to correct for that. All right, so I have a GCF over here. I'll pull it out. X squared minus 2x plus 1. I have a GCF over here, also a -1, so minus y squared minus 6y plus 9, and then minus 1. All right, -11 plus 10. All right, so it's like, all right, what's the benefit of all this? All right, just stay with me. Negative x minus 1 squared minus y minus 3 squared minus 1. All right, this is actually the justification for why -1 is the largest number, the largest z value. Again, just I go back and forth. F of x comma y is the same z equals. All right. So what I'm doing here, and I'll write it slightly differently. I'm taking -1 and I'm subtracting something that's positive. And then I'm subtracting something else that's positive. This is a positive number. This is also a positive number. Therefore, the largest z has to be equal to -1, because if I, just pick any 2 positive numbers, start with -1, and then take 2 positive numbers and subtract them from -1, you're going to get something that's more negative. All right. If I made it a 2 and a 3, -1 minus 2 minus 3 is going to give me a -6. That's smaller than the -1. No matter what I plug in for x or y, I'm always going to get something smaller than or equal to that -1, because these two could zero out. The only time they ever zero out is if x is 1 and y is 3, which is what we came up with as critical values before. So those critical values are justified as being the location of a relative extremum, specifically 1, 3, -1. Question?
We were able to do that because we made this look like an open disk, so that's like the formula for a circle. So we could say it's going down with a positive value. What if it didn't look like an open disk? What if it was some random equation?
That's the next part of the
ln
lesson.
of x.
Next part of the lesson.
Okay.
Yeah, there's properties and rules that come into play when this doesn't work. Because this is ideal. Okay, it doesn't look like it's ideal. But this is the best case scenario. Now, you just kind of wrap your brain around that idea for a second. Like, half a page worth of work is the best case scenario when it comes to this.
And we got the 1, 3, -1, and we didn't plug it in the derivative because it's 3D, correct?
We didn't plug it into the derivative.
I remember in Calc 1, we plugged it into the derivative to find out.
Oh, like in a sign chart?
Yeah.
Yeah.
Find the x and y.
Yeah, we wouldn't need to do that. Yeah, we're going to use a different approach in a sec. All right, so,
Oh no.
yeah. Critical points of the function, cosine x, sine y. All right, so if you were ever wondering what the equation was to generate those like egg crepes, like you put eggs in them, that's what it is. Or mattress toppers, right? Yeah. You'd it's cosine x sine y. Or cosine y sine x. All sorts of possibilities get you the same thing.
Or cosine x, cosine y.
Or cosine x cosine y. Sine x sine y. So all sorts of things. All right. So tangent's fun.
Which looks like a series of like cones and
Like
stuff like that. Yeah.
So critical point, because I think we'll all agree when you look at it, cosine, sine, they're both continuous everywhere, so we're not worried about that. So derivative. So partial with respect to x. So I'm going to hang on to the sine of y. Cosine x becomes negative sine x. Partial with respect to y. Hang on to the cosine x. It's going to be cosine x, cosine y. All right, so I'm going to set those equal to 0 and solve. So we have two factors, set each one equal to 0. You get sine x equals 0, sine y equals 0. Now, this is an or situation. I'm just going to tuck a little or in there. All right, maybe I'll do that in a different color so it actually stands out. Because it doesn't have to happen simultaneously. In order to get the partial with respect to x equals 0, either one of these needs to be equal to 0. If they're both equal to 0, great, but they don't need to both be equal to 0. All right, same idea for the cosines. All right, so cosine x equals 0. Cosine y equals 0. All right, so think about the unit circle, and you think about instances for which the sine function is equal to 0. That happens along the x-axis. So we're talking about x has to be equal to 0, pi, 2 pi, and so on. Y has to be equal to 0, pi, 2 pi, and so on. Cosine has to be equal to 0. Oh, I already wrote the cosine. Pi over 2, 3 pi over 2. Maybe some negatives if you want, but let me just focus on the positives. 5 pi over 2, and so on. Same thing for the y's. All right, so I tucked a little and symbol in there. Actually, I'll do that a few steps of the way here, because they have to happen in conjunction with one another. The partials will never be undefined, so I'm not worried about where they would fail to exist. I'm only worried about where they'll be equal to 0. All right, so I need to pull from these values that would allow this partial and also this partial to be equal to 0, right? So now it's just a matter of, I don't know, itemizing everything. Right? There's a lot of stuff to go through here, and so it's just a question of, do I have everything that I need? All right. So now the one issue here, or one main issue, is that each of these functions consists of both an x and a y. All right. So we just got to be careful that we're not going to run into any domain issues. And when you're dealing with sines and cosines, that's not typical. It's not something you really need to worry about. But just for other types of problems, you want to be mindful of that. All right. So as far as ordered pairs are concerned, 0, 0 will do it.
I'm sorry, does that mean that any combination of any x and any y will result in a critical value?
Not necessarily. So that's what we're going to do. We're going to go through each one of them and test them out and make sure that they both lead to both x and y values that I choose will lead to both partials being equal to 0. So, for example, 0, 0. Well, 0, 0 and whatever the z value is associated with that. So, I know it's going to work here. If I plug in a 0 for each part, it's going to give me a 0. If I plug in a 0, because once I've decided that I'm working with 0, 0, that's going to be, I mean, it could be good or it could be an issue. On this side, it's perfectly fine. But if I'm going with 0, 0 here, it better work over there because they both need to be equal to 0. So if I plug in a 0 for cosine, I get a positive 1. In both cases, I'll get a 1. 1 and 0 are not equal. So this would actually be a bad ordered pair, right? Because it needs to work for both. All right? So then I would try 0 pi. All right? So if I plug in a 0 and a pi for that, because it came from this set, we know it's going to be fine. But will it work over here? If I plug in a 0 and a pi, that's no good. All right? It's going to give me the same issue. All right? So it's not going to work for both. If it doesn't work for both, it's no good. Has to make both partials equal to 0. All right? So then 0, 2 pi, no reason to expect anything else will come from this. Right, so then we start mixing and matching between the two functions. All right, so we take an x from one set and a y from the other. All right, so this one didn't play out, so I'll get rid of that. So then what I would do is I'd go with 0 and pi over 2. 0 for x, pi over 2 for y. All right, we know the 0 is going to be fine over here. The pi over 2 is going to be fine over there, so we're good. All right, so I'll take an x and pair it with each one of these y's. Any one of these x's along with any one of these y's will be perfectly fine.
And then vice versa, right?
And then vice versa. All right. So we would have x of 0, y of pi over 2, 0, 3 pi over 2, 0, 5 pi over 2, and so on. So instead of writing that, let's just pare it down to say 0, comma, pi over 2 plus pi k. All right. Now, if we know that that's also going to work for the pi, 2 pi, and so on, then we could even extend it further by saying, all right, wait a minute. It's really not that as much as it's saying, because we can focus on this guy and say it doesn't have to be just that. It could be any of these. So we would say 0 plus pi k, comma, pi over 2 plus pi k. And then the z's associated with all of those. All right, so I'd have to write, this is ugly, but f of 0 plus pi k, comma, pi over 2, sorry. No, actually, no, that was right. Pi over 2 plus pi k. Now, here it's only asking us to to investigate the critical values is not asking us to state what if any, the max and mins are, because there's also the possibility, just to make this as mind-bending as possible, some of these might play out to give us a max, and some of them may play out to give us a minimum, right? And how we juxtapose them might impact things, but that's beyond the scope of the question. All right, so the other way around would be to say this group of x's with that group of y's, in which case I would say pi over 2 plus pi k, 0 plus pi k, or just pi k if you want, and then f of all that. All right, and so just to talk you through the remainder of it, because honestly I don't remember what I put in my answer key online, but I might have gone a little bit further. The idea would be, if you needed to determine a max or min, you would plug them back into the original function, because these are periodic, which means that once you've established what a maximum is, it's going to be the same, it's going to propagate throughout. So let's say, for example, I wanted to go with pi over 2 for x and 0 for y. If I do that, then I'm going to get, I'll get a 0, right? In the original function. All right, so that would actually be a saddle point, right? Because that's neither max or min, so we would call that a saddle point, right? If I did, let me see if I can find one that works. I need one of these guys. Actually, they're all going to be, all of these are going to give me saddle points. Oh, no, this set will give me extrema. Because if I put a cosine of 0, that'll give me a 1. Sine of 1/2 would give me a 1. So at 0, 1/2, I'll have a z value of 1. 0 pi over 2 is what I meant to say. I'll have a z value of 1. If I did pi and 3 pi over 2, same deal, I think. Negative, negative, so positive. Yeah. So we would be living with maximum values there. But you could test them all out, you know. But again, beyond the scope of what the question's asking, because there's other ways to do this that don't involve us testing all possibilities.
Well, I was going to ask that without looking at GeoGebra, how do you know that the max value would be 1? I mean, in this case, because it's cosine and sine, it repeats itself.
Right.
But like,
once you've come up with your array of critical values, you know that the max or min has to come from that set. So then, worst.
Tons of sets.
Right, but there's the periodic nature of it. Like when you're dealing with something like this, you're not going to have too many possibilities. But when you're dealing with something like this, yeah, you have a ton of possibilities, but many of them repeat themselves. So once you've gotten a full collection of all possibilities, you figured out what x and y combination gives you a positive 1, gives you a 0, and what gives you a negative 1, then you've accounted for pretty much everything. And so you could just move on from there. All right, numbers 3 and 4 are much easier, so I'll put stars on those. The next class I think is going to be a star-studded class, because I have some star problems from the last class I taught, and then these new stars. Partial with respect to x, negative 2x. Partial with respect to y, 2y. All right. So what we're looking for here are critical values, and critical values occur when the partials are equal to 0. And equal to one another. All right, so in this case it works out and we're looking at 0, 0, sorry, 0, 0 as being a critical value. All right. So, sorry, I got a frog in my throat. So if I want coordinates, all right, so the order triple related to this, it would be 0, 0, 0. All right, so 0, 0, 0 would be the order triple. All right, this would be f of 0, 0. All right, so now that's cool. It's just a question of, well, what is that? Is it a relative max, relative min, or is it a saddle point? All right, so how can we figure it out without the second derivative test? Well, there's a couple of ways. But the easiest way would be to take a point or points that are around 0, 0, 0 and see what it gives you. You know, so what I would test, for example, I would test 1, 0. If I test 1, 0 in this original function, plugging in a 0 for y and a 1 for x, I would get a -1 as a result. All right, and what that tells me is that this point 0, 0, 0 is not the lowest point on the graph. All right, so 1, 0, whatever is a point that's close to 0, 0, and it gave me a result. It gave me an order triple of 1, 0, -1. That's a point that's definitely below on the z-axis, below 0, 0, 0. So I can write it as the order triple 1, 0, -1. All right, so this is not a min. All right, so then I might try something like the other way around. Maybe I'll try 0, 1. If I try 0, 1, plugging in a 0 for x and a 1 for y, I get a +1. That gives me an order triple of 0, 1, 1. Which tells me that 0, 0, 0 is not a max either. Because compared to a point that's very close to it, it has a smaller z value. All right? So it's neither a max nor a min, therefore it must be a saddle point. All right? So you might look at this and say, well, why on earth would we do it this way when we have a second derivative test? If you're thinking that, then perhaps you don't remember the second derivative test. All right? You could do this with the second derivative test, and you know, it'd take you a few more lines of work, but you would need second order partials, you need a discriminant, and then you need all the rules related to discriminant to help you determine whether or not it's a max, min, or a saddle point. Right? But for this kind of situation, just by simple direct observation, you're able to make a determination that it is a saddle point because it's neither a max nor a min without having to go through all that stuff. All right, so it's an option, right? Whereas in number 2, after all that mess, you might have wanted to use the second derivative test because we had a lot of craziness going on with that one. But for this one, it's much simpler to do it with direct observation. All right.
Isn't that just luck, though? Wouldn't we have to do the second derivative test? Because
It's not really luck. What it is, it's making a, yeah, you're using a computational method. It's kind of like finding a limit without, so instead of just jumping into all the algebra, you say, well, let me just try to plug the numbers in and see what I get. And then you end up getting an answer that actually works. So
what I was thinking, though, is that what if there was a max, and what if you had 2 maximum points?
then you have to go to the second derivative test.
You would have to.
Yeah. So you take a shot in the dark, hope that it works out. And then if it doesn't, you still have the second derivative test. It would be luck. I would define it as luck if you were to say, forget this whole second derivative test. I'm not even going to bother learning it because I'll just do this every time. And to count on that to work, that would be irresponsible.
So that's sort of along the lines of what I was gonna ask. Like, let's say you had, like in this function, you have a lot of options to pick that will show you that there's higher and lower points in the local area. What happens if there was that are in the majority of the circle, and you say, oh, it's a maximum.
That would be problematic.
Yeah.
Like, I feel like you could do this only because it's a simple equation, y squared minus x squared. But if you got something like e to the y, l to the x, some random.
Not even that. It really doesn't relate to the difficulty of the equation. It has to do with the outcome. It really, the best case scenario is when it shows that it's a saddle point. Using this method to really justify that something is a max or a min, that's, I mean, you're taking a chance.
Oh, okay. So if you got the first test that was equal to 1, second test is equal to 1, and everything was equal to 1, it's like, dude, okay, I don't know what this point is.
Yeah, then second derivative
I
test.
have to do this.
Yeah. All right. So that's really the idea there anyway. So yeah, so we'll take a look at number 4 and we'll see. So first order partial with respect to x. All right, so we get that, right? Because the derivative on the inside is just going to be equal to 1. If we do the same thing for or with respect to y, we're going to get the same result. We're going to get partial with respect to y is going to equal 1/2 x plus y to the negative 1/2, which amounts to, and we kind of dealt with this before, 1/2 root x plus y. All right, so when we go to set each of these equal to 0, you don't get anything. All right, there's no solution when it comes to that, but you can get cases where it's undefined. All right, so that's the other condition behind a critical value, the idea that the first order partial or with respect to x or the first order partial with respect to y can be undefined, and if they are, as long as the original function is defined for those particular values, then you'll have critical values. All right, so what I would do is I would take my first order partial and set it equal to 1/0, which is the same as saying 1/2 root x plus y is equal to 1/0. Root x plus y is equal to 0, in which case we're getting, really, I mean, you could divide out the 2, right? You can square both sides, in which case you get x plus y equals 0, right? And ultimately you get a relation between x and y, right? Y is equal to negative x. All right, and that would be the same for the other one, right? So this is also true for partial with respect to y. All right, so what this is telling us is that we have critical values along y equals negative x. All right, so along that plane, the intersection between that plane and the function that you were given. All right, so every one of those would represent a critical value. All right, whether or not they represent a min or a max is a different story, but I mean, we've talked about this before. You can't always rely on having a diagram. In this case, it looks like it comes to an abrupt stop here, in which case it would be a low point. But if that's the case, then really what are we talking about? You can call pretty much anything a minimum under those circumstances, because if I restricted domain, then everything would be, or at least come to a final conclusion, I suppose. You know, it would come to a dead stop somewhere, at which point you would call it a minimum or a maximum, but you wouldn't necessarily call it a relative min or a relative max. Right? So all we can do for this kind of question is make a determination of what would give critical values, what relationship, but we can't make a determination beyond that. All right. One thing we should also account for is the domain. all right? And that's the case where x plus y is greater than 0, greater than or equal to 0, sorry.
It can't be equal to 0.
It can be in the original.
In the original, yeah.
Oh.
So y has to be greater than or equal to x, negative x, in order for the function to exist to begin with. All right, so if that's the case, then we would actually have to make a statement, because if the function, well, no, we're good. I was going to say we'd have to make a statement, but only if it were greater than. So we're good. The critical values can still exist along those points, but it would not necessarily lead to a relative extrema. All right, so that's a Calc 1 idea, where just because you have a critical value doesn't mean you have a relative extremum. But if you have a relative extremum, it must be a critical value.
So is there no way to calculate global minimums or maximums?
There is, and we're getting to it. Yeah. Oh, this is what I was waiting for. This is the connection between multivariable calc and statistics, which is really exciting. So you may have heard of linear regression, hopefully. I mean, it's not something that you need to take a stat class in order to have seen. I mean, if you've gone through like school, you've done a linear regression at some point, like middle school and high school, and maybe some you touched on it in college. I don't know. It depends on the teacher. Definitely, if you took a stat class, you definitely did it. All right, but you've learned terms like line of best fit, linear regression equation, and things like that. Maybe you got into things like quadratic regressions and all that good stuff. The good news is we don't really have to deal with quadratic regressions or anything like that, because really they're just a transformation of a linear regression anyway. So, so yeah, it all comes back to understanding of linear regressions. But the fun thing is, or the fun aspect of this, is that these formulas that you may have seen in a stat class, you definitely see them in a stat textbook, right? So it's one of those things where if you had a stat teacher like me who is like, all right, here's some cool formulas, we're never going to use them, take out your calculator, activate it utilizing the on key, and then go from there. But I mentioned this last class that my first few years teaching stat, I didn't know the calculator could do all this stuff. So I was like, all right, well, I guess we got to just dive in. And then I found out that the calculator, the TI-83, 84s, were built specifically for statistics. They added on like all calculus stuff later on, right? So, yeah, I was like a pretty big fool after that. But these formulas help you find the slope and the y-intercept for a linear regression equation. So if you're given an array of points, by determining the result of these formulas, you would get the line of best fit. Now, I would tell my stat students all the time, you'd have to take a calc class in order to understand where these formulas are coming from. And they're satisfied with that, right? And you'd be satisfied with that right now also, I think. You'd be like, yeah, you got to take a calc class in order to understand this. You'd be like, okay, cool, I'll make sure to do that. But the idea is that it came from the knowledge of partial derivatives, and it's a pretty cool relationship. Right? So what we have here is the sum of the difference between the y values that are given and predicted y values, and those values would be squared. So what's really happening is a line is placed. All right? So go back to middle school in your mind and put a ruler in a place that you think best approximates the line that would fit the data most appropriately. All right? Then what you would do is find what we call the residuals. the difference between the y values and the predicted y values. So any y value that you had on your line would be a y hat. Any actual y value for a coordinate is the y, right? So what we want to do actually is minimize the distance between y values.
Why are we squaring?
Well, it's actually the least squares regression. The idea behind that is so that you can, when you take the sum of all those distances, you can have positive values to work off of. Because what will happen is you'll have maybe a positive deviation here, but a negative deviation there. If you add them together, it would go to 0. And if you're not careful, you might think that all the points fall on the line perfectly. So one technique to handle it would be to take the absolute value of the differences, but the other technique would be to square it or raise it to any even power. The idea, and this is really something that even goes further in calculus, is the idea that while you can take the absolute values, that doesn't fit a normal distribution, right? So everything revolves around the concept of a normal distribution. When you're talking about deviations, standard deviations, things like that, it all goes to a normal distribution, which works perfectly when you square the binomials. It doesn't work at all if you take the absolute values. All right, so it's kind of like the consequence of this that drives why we square it rather than just taking an absolute value. But this relationship is why they call it the least squares regression, right? Because I want to minimize the squared distances from the y value that we have and the y value that is predicted based on the line. All right, so the question would be, well, how do we do that? Well, we have the linear regression equation that we want, complete with the slope and the y-intercept, slope and y-intercept, and then I have the equation that I want to minimize. All right, so what I'm going to do is define this equation as some function, and that function, because I'm really looking for the slope and the y-intercept, it's going to be a function of BO and B1. Now, the y hat, we're defining that as BO plus B1 x sub I. All right, so the x sub I and the y sub I values, those are particular numerical values from a data set. All right, so you're given a raw set of data that's consisting of coordinates. Those coordinates have x values and y values. The subscript of I just represents the position within that data set. So if I said x sub 1, y sub 1, I'm saying the first x value and the first y value. If I said x sub 3 and y sub 3, I'm talking about the ordered pair, the third x value and the third y value. All right, but ultimately, they're particular numerical values. So what that means for us is that we're treating them as constant. All right, everything else is variable. All right. So what I want are, they're going to be partials. I'm going to need a partial with respect to BO and a partial with respect to B1. But before I do that, I do want to clean this up a smidge. I don't want to distribute the binomial to the second power, but I do want to just run through with that negative. Those double parentheses would drive me nuts after a while. All right, once we've stated what the bounds of the summation are, it's going from 1 to n, we don't have to write that every single time. We only write it when it's relevant now. All right, so I need a partial with respect to BO. So it's power rule. 2 times the sum y sub I minus BO minus B1 x sub I to the first power times constant, right? So it's going to 0. I'm taking the derivative partial with respect to BO, so the only thing in here that I'm treating as a variable is the negative BO.
So -1.
So -1.
Is that being inside of our summation or is that outside?
It's inside the summation, yeah. All right. Now it is a constant multiple, as it turned out, so it doesn't really need to be there. So I can actually pull it out with the negative, with the 2 on the outside and make it a -2. And in fact, well, I'll tell you what the in fact thing is in a second. Hold on. In fact, the only things that really need to be inside the summation by rule are the x sub I and the y sub I. Because when you have a summation, the only things that are relevant to it are the elements that contain an I. Right? So if I can actually remove the BO and the B1, that would be great. Right? As it turns out, I can, but let's take the next step real quick. The next step in this process, we are trying to minimize. So I want to find critical values. We're not concerned with where it would be undefined because this doesn't look like anything that would be undefined based on a radical or a denominator or anything like that. So I can just go ahead and set it equal to 0. I can knock off the -2. It doesn't need to be there. One of the very early rules related to summation, it wasn't even Calc 2, it was even before that. Because if you had a sum containing a sum or difference, you could find the sum of each element individually. Right? So what this would end up being is the sum of y sub I, and we could say plus the sum of negative BO, or I would prefer to write minus the sum of BO minus the sum of B1 x sub I. All right, and we could take it another step in a sec. That'll help us clean it up pretty significantly. Right, because again, the idea, you don't have to write it every time. You don't have to write I equals 1 to n every single time, but you should be aware of it. And the reason you should be aware of it is the idea that the only thing that needs to remain within the summation is an element that contains an I. All right, so the sum of yi needs to stay put. The b sub o, that could come out. I can write this as negative b sub o times the sum of 1. And I'm going to put the index and all that good stuff on it in a second just to really kind of drive it home. But also I have a constant multiple, or I'm sorry, a multiple of b sub 1. It's not constant, it's what we're treating as a variable. I can pull that out also. So minus b sub 1 times the sum of x sub I. What's that?
Why are we back to treating b sub 1 as a variable?
Oh, sorry. It's a variable. We're not treating it as a variable in this context, but it is a variable.
Okay. So how can we extract that and not the x if it's not being treated as a variable here?
Well, that it has more to do with the fact that it doesn't contain an I.
Okay.
All right. So just going back to that, you can say I equals 1 to n. I'm just really going to focus on this one because I can simplify that part of it. The other ones we're stuck with, but when you look at what we're supposed to end up with in the end, that's okay. Right? We're supposed to end up with a ton of sums of x's and y's in various forms, even an n in a couple of different places. So it's fine to have these guys. Some other things need to go away. I don't see a sum of 1 in there. But, and this would be great, does anybody know what the sum of 1 is from I equals 1 to n?
1.
N. But you said it with enthusiasm, and that's all that matters in the end.
I thought because there was no n there, it's, you know.
But even though you're incorrect, I was super nice about it.
Thank you.
No problem.
There are only people in this class right
Yeah. Yeah. The claws come out. It's like razor sharp. Yeah, so if you have the sum of a constant, you just multiply it by the upper bound.
Okay.
And that's all there is to it.
So if it was a 2, it is 2n, right?
Correct. Correct. Now, that being said, if it's the sum of 2, you could actually make it 2 times the sum of 1, in which case you could still work off of this very basic rule, right? This is one of those rules where I think you can probably kind of invent it if you needed to. Let's say, for example, the upper bound was 5. You would say, okay, all right, I'm going to expand this. It would be, I'm gonna write the 1 5 times and then add them up. I'd get a result of 5 when I add it all together. Right? If I had an upper bound of 20, I'd write the number 1 because there's nowhere to substitute in. I'd write the number 1 20 times and then add them up. I'd get 20. Right? So you could probably just kind of invent it as needed. But if you know the rule, that's even better. Now that's actually the only rule from summation that you really need to know here. All right, so that's good news. Look at all that. It's fancy. There is more. There has to be more. Look where we have to end up.
now. Not even close.
Yeah.
Oh wait, there's more.
Oh wait. Don't you worry. So we can continue with this and solve for one of these two variables, whichever one we decide is more convenient. One of these two values, B0 or B1. It really doesn't make a difference, but I want to go through the partial with respect to B1, see where that goes before I make a decision on what I want to solve for here. All right, so back to scratch. So I'll just kind of chuck it in over here, F sub B1. All right. So really, if you do a quick comparison between our first order partial with respect to BO, you're going to have a lot of similarity because it's chain rule. It's going to be the same stuff, but what we multiply by at the end is going to be different. All right. So 2 times the sum of y sub I minus b sub O minus b sub 1 x sub I.
Isn't the x sub I supposed to be a variable?
No, it's constant.
Still a constant.
Yeah. So we're going to take the derivative of the b sub I, b sub 1 term, because these two guys are now treated as constant. So this is the only variable component.
So it's still minus. It's still minus.
Not 1.
X sub I.
X sub I. Because x sub I is the constant multiple. All right. Yeah. So, continue along this thread here.
Set it equal to 0.
We could set it equal to 0. Let me just do that right away. I'll write this as negative x sub I multiplied by all that good stuff. So the 2 goes away, which is one. Oh, the 2 was gone to begin with. Sorry, I don't even know why I wrote it. Because of the whole, you know, chain rule and math and stuff. I was about to fake my way through the rest of this solution. Well done. Well, then you could be a math teacher. So we're looking at, I will run through with the negative x sub I. So distribute negative x sub I, y sub I, plus b sub o x sub I. I'm just going to say b o x I. This is getting out of hand. Plus b1 x sub I squared. Although I like saying x sub I. All right, we have a sum containing sums. So we can break it up, just like we did on the other side. So barring anything too catastrophic here. Just doing a quick double check Ruski here. Make sure I wrote it all correctly, because now we're going to get into the substitution part of it, and I don't want to be working off of a mistake. So negative sum of x sub I, y sub I, plus b sub o times the sum of x sub I, plus b sub 1 times the sum of x sub I squared. All right, so now we're at the point where we can try to do something here. Just a question of what. So we have two equations that ultimately need to come out to give us these bad boys. So it's just a question of what we want to substitute where. All right, so I have a negative b sub 1 times the sum of x sub I. Not quite a direct substitution, but maybe we could do something with that. Here I think it's probably easiest to solve for b sub o. So that's ultimately what I'm going to do. And then replace the b sub o in the other equation, right? So, because really it's just a matter of bringing this over and dividing by the n. So in terms of just keeping things clean, that's probably the best way to do it, right? So b sub o is going to be equal to, we have the sum of y sub I minus b sub 1 times the sum of x sub I all over n. All right, so all I did was I took this middle term, swung it over to the other side, and then just collected these two bad boys, divided out the n. All right? So now I have the ability to directly substitute, and now have an equation that's solely in terms of b sub 1. All right, so we're going to swap this out. So we're looking at, let me just bring it over, not too far. 0 equals negative sum x sub I, y sub I, plus, here we go, sum of y sub I minus b sub 1 times the sum of x sub I over n times the sum of x sub I plus b sub 1 times the sum of x sub I squared. There's more. There's more. Hold on. We could do a couple of things at this point. I think probably the easiest thing to do would be to run through with an n to clear out that denominator. Not sure why I needed to stand up for that.
Multiplication, like, can you change that first term into the sum of x sub 1 times the sum of y sub 1?
You could, but ultimately we need that.
Okay, but then you could just factor out and x would that give up give that?
I don't think so. If we multiply through with an n, things are going to start cleaning up nicely, surprisingly nicely, fairly quickly. Now this, I just need to make sure. Yep. Yeah, that middle term is losing the n, and the last one is gaining an n. All right, because it was, let me just make sure, yeah. It was the entire b sub o multiplied by the sum of x sub I. So since there's a binomial here, even though I wrote it as a separate thing, once I cleared out that n, this became a binomial that needed to be multiplied here. So we don't want to lose sight of the fact that we have to distribute there. All right, so next step, negative sum of x sub I, y sub I, plus, we're multiplying the sum of x sub I and the sum of y sub I. So that's going to give us a sum of x sub I multiplied by the sum of y sub I, which you can combine if you want, but I'm going to leave them separate. Minus b sub 1. For the other one, there's really no reason not to put them together because it would just be the sum of x sub I squared plus n b1 sum of x sub I also squared, but different kind of squared. This is a case where you would find the sum of all your x values first and then squared. Here you would find all of your x values, square them, and then add them all up after the fact, right? But the good byproduct of this is the fact that now we have the ability to isolate the b sub 1, right? So I can move these two terms to the other side of the equation and then factor out a b sub 1. So we're looking at b sub 1 times the sum of x sub I squared plus minus n b sub 1 times the sum of x sub I squared equals everything else. All right, so sum of x sub I multiplied by sum of y sub I. I'm going to write minus n times the sum of x sub I, y sub I. All right. So we have the GCF of b sub 1 that we could pull out. And then once we do that, we can divide out everything else. So
Isn't the GCF b sub 1
Well, these are two separate terms. So it's not a common factor. So they're not equivalent to one another.
Why?
Because this is what you would get if you were to take the sum of all the x values first and then square them. This is what you would get if you were to square all the x values first and then take the sum. It's not a commutative operation when it comes to summation. Also, more importantly, I think, ultimately we want to solve for b sub 1. So just by pulling out the b sub 1, we're going to get there quicker. All right, so sum of x sub I times the sum of y sub I minus n times the sum of x sub I, y sub I, all over the sum of x sub I squared minus n times the sum of x sub I squared.
Wait, there's more.
No, that was it.
B sub 0.
Well,
Well, there's the b sub 0 part.
but that's the b sub 1.
But this is the b
right?
sub 1. We just have it backwards. But both parts are backwards.
So this is what happened.
Both part? No, just the top part is.
Yeah, but it's not half of it in that we have to do another page worth of work. It's half of it in that we came up with one equation as opposed to both of them. So in order to come up with a second equation, we go back to this one and replace the b sub 1 with that whole jammy.
Oh.
We ran out of paper.
Oh, I have plenty.
We can try it out.
So this is the one and only question on the final, right?
If you're one of the lucky few that gets to take the final, you will enjoy some variation of a question like this, yes.
Why is it on the same not in simpler? You can combine that x1 and y1. The simpler that term times 1 minus, or n minus 1 or 1 minus
And
7.
now we're doing b sub 1.
N minus 1 or
Like,
1.
I'm just saying, compared to the reference, what we're trying to prove, the numerator.
I mean, it's pretty much the same.
One has,
I just
Well, we
did
said
it
that
the other way around.
b sub 1
No, I'm
equals
saying,
that, so that we just set that equals
why,
0, so that we can solve it.
why instead of,
Now we're
like, why are we
taking it to
writing the e to the xi and yi twice instead of factoring it out?
Not sure I follow.
In the numerator, you have a sum of xi, yi, right, minus n times that same value.
Oh, yeah, these are not equivalent. Because this is the product of all the x and y values with the sum taken after the fact. And this is the sum of all the x's numerically, you get a value, and then the sum of all the y's numerically, you get a value, and then multiply them together.
Oh, because when I asked earlier, you said they were equivalent.
Oh, I did. Oh, I misspoke. I apologize for that.
That's fine, I just have to rechange all my notes.
You have to what?
I have to change all of my notes because I've been combining them.
Oh, no. So you, instead of writing down what I'm writing down?
Like, I didn't write that. Do I want to write that E as many times? No, because I can't write it.
Oh. Well, now you get to write everything again.
That's tough.
Tough spot to be in. So, there we go.
This is a really bad.
Oh, so you're plugging. Oh.
Oh.
Oh no.
B sub O is equal to all this.
This is really slow.
Oh, wait, there's more. All right, so all that
All that over
multiplied by the sum of x sub I all over n. Yeah, so all we have to do now is find a common denominator, and everything will be fine. So, nah, we don't have to find it. It's right there. So we're going to have this baby getting multiplied by that bad boy. Minus so we'll have the sum of x sub I multiplied by the sum of x sub I. That's fun. Sum of x sub I squared. Times the sum of x sub I multiplied by the sum of x sub I y sub I. Oh, get out of here. And then the whole shabiggity bang here is going to be over n times the sum of x sub I squared minus n times the sum of x sub I other kind of squared. So, almost there. Like a step away, maybe two. Just doesn't seem like it would be. Because when we distribute, we're going to get, and I'll show the distributing, the sum of x sub I squared times the sum of y sub I minus n times the sum of x sub I squared times y sub I, the sum of y sub I, minus the exact duplicate of the first part. So, except opposite. All over 2A. It's not 2A. All right, we'll find out in a second if I screwed up something algebraically, but we do have this with this, and then we have a common n that can be pulled out. So we're looking at, so looks like a negative n. I'll pull that out of the whole top. the sum of x sub I. Yeah, but then we wouldn't have anything to cancel it with, so I just figure leave it there. Alright, so the m's cancel. Still left with that negative there. But I could associate the negative with the bottom and make it the sum of x sub I squared, sum of y sub I, plus the sum of x sub I, sum of x sub I, y sub I, over n times the sum of x sub I squared minus, yeah, I'm switching it around. Squared. I don't know, is that right?
Yep.
Hey! Oh, there it is. See, it looks exactly the same. See? Identical.
Is this what happened to you when you figured out how to calculate it?
Yeah. I had to.
Now you chose an easy way, right?
This is a proof. There's no easy way.
Unfortunately, that was the easy way. Test. All right, in Calc 1, that didn't strike fear into the hearts of people everywhere. The idea of a second derivative test. You just take the derivative a second time. But in Calc 3, we know second order partial is like, we want second order partial with respect to x or y or mixed second order partial. Oh, geez, which one do you want? So, very procedural. The issue, though, is it's not a short procedure. Right? And not short in actually reading through it and not short in carrying it out. Suppose that f(x,y) is continuous second order partial derivatives, some open disk containing the blah, 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 blah. All right, so you have critical values. The continuous second order partial derivatives, that's like a throwaway statement from Calc 1, but here it's so important because what it means is that your second order partials are interchangeable. All right, so partial xy is the same as partial yx, right? Because it's continuous second order partials, right? If it were not the case, then this all falls flat, all right? We define the discriminant, all right? So we get our critical values, still got to do that, but we define the discriminant by this formula. Second order partial with respect to x, then y, then the mix. We'll talk about where that comes from next time. Once we get that value, it's kind of like discriminant sort of from quadratic formula, where you have conditions associated with the type of value that you have. If your d is positive, and so is your second order partial with respect to x, then you have a local minimum at AB. If only the d value is positive, but the second order partial with respect to x is negative, then it's a local max. If you have a negative d, this is the one that you're hoping for, because that means, well, actually these two, kind of. 3 is really the one you're hoping for, because it's the one where you could draw a conclusion by doing the least amount of work. Your d value is negative, then that means there's a saddle point. It's neither maximum nor minimum. Critical value doesn't lead to a max or a min. The d equals 0, it depends on the question. If it says use second order partials to draw a conclusion about or classify the critical points, then that's fine. But if your objective is to find the critical points and then find extrema, and you get a d equals 0, there really is nothing more frustrating. Because what that means is, well, maybe it's a max, maybe it's a min, or maybe it's neither. I can't conclude based on what we've done, which means I wasted all my time doing that, which is brutal. All right? So definitely something to be avoided. But anyway, let me find my first order partial with respect to x. 4x cubed minus 4y. And my first order partial with respect to y, 4y cubed minus 4x. All right. Now these have to be equal to each other and equal to 0 in order to have a critical value, right? Or if either of them don't exist, but so far continuous differentiable all the way through. So I'm going to set it equal to 0. I'm going to clean it up. I'll make this y equals x cubed. All right, the other one, same general idea, except it's x equals y cubed. All right, so we have a relationship here. That's something. Doesn't seem like an overly meaningful one until, well, this is the geeky math teacher inside of me. Well, inside of me, that's who I am. So it's this and that. So that's the definition of a system of equations. Two equations that are true simultaneously. So I need y to be equal to x cubed at the same time that x is equal to y cubed. If that's the case, that allows me to substitute from one equation into the other. So I can replace, for example, the x cubed here. I'll replace the x with a y cubed and make it y equals y cubed cubed, which means y is equal to y to the 9th. All right, now just be careful because Algebra 1 students do this and Calc 3 students do this too. You can't just divide out a y. You're going to lose a solution. All right, so bring over the y to the 9th minus y equals 0. Factor. And solve. You get y equals 0, y to the 8th minus 1 equals 0, which means y to the 8th equals 1, which means y is equal to plus or minus 1. All right, so we have 3 potential y values, which correspond to 3, well, possibly 3 potential unique x values. All right, so x is equal to y cubed. So if x is equal to y cubed, and we have these 3 y values, then we would get ordered pairs. If I plug in a 0, I get a 0. If I plug in a 1, I get a 1. If I plug in a -1, I get a -1. And these would all have z values associated with them. But again, instead of plugging and chugging away, well, the first one I can do. 1. Well, actually, I guess I could do them all, because these are easy numbers to work with. So 2 minus 4 is -2, plus 1 is -1. Two, so it's same deal?
Yeah, same deal.
Same deal, right? All right, now it's hard to see this diagram, but it does look like kind of like a pair of pants, sort of. So it comes down and then it goes up. I'm not going to describe what that area is. And then it comes back down to the other pant leg. And then, so you have what appears to be a couple of minimum values, and then up in that area, that could be a maximum, or it could be a saddle point. So, yeah.
But I'm sorry, what would be the maximum? Or the minimum?
These two these
But
two
without
vectors.
that picture, that's my point. That's like,
That's why we investigate using this approach. Because if you don't have the diagram,
Oh.
then you can't even go by that. So at this point, if that diagram were not there, I'd look at this and say, I have three possible coordinates that could represent three possible things. Min, max, saddle point. I don't know what's what. All right, so what we do is we figure out the discriminant for each one of them. All right. So I need my second order partial with respect to x, which requires me to see my x, 12x squared.
You did not give us enough room for these problems.
You just write way too big. I like font 6. That's all.
Yeah, you just got to dial back your font. I mean, I figure if I spot you the first 100 pages and notes, or you can go to notebook pages every once and again. F of yy, f sub yy, that's going to be 12y squared. So I need, for each of these xy pairings, right, I also need the mixed second order partial. So f x y. So I'll take my x model and do it with respect to y, which is a little bit easier, a lot easier. It's just a -4. So that's nice. All right, so again, I'm going to evaluate each of these for each of the coordinates and see what my d value is. All right, so I'll do it right here. Oh, sorry. So plugging this in for x and y as applicable. All right. So 0 times 0 just trying to be able to point to the formula. So plugging the a, b values into the second order partial with respect to x, it doesn't call for a y, so I only have to plug in the x value. The f of yy, oh, that should have been a, no, it's still a 0, because I'm plugging in a 0 there. But then we're going to subtract the -4 squared. So subtract -4 to the second power, and that's going to give me a 16.
-16.
-16. All right, so then I'll do the same thing for 1, 1. And then we'll do the compare and contrast all in one shot. So 12 times 12. And it's going to be the same deal because the second order partial with respect to y, the mixed partial, is still -4. It's constant. So we're still going to have a subtraction of 16. So 144 minus 16 is what, 128? And then I do the same thing for -1, -1, and that's going to give me the same result, right?
Yeah.
All right. So, looking at my conditions, I always go for the saddle point first. All right, saddle point is the easiest one to identify. If your discriminant is negative, then you have a saddle point. All right. So my saddle point is at 0, 0, 1. In the case of the second two coordinates, I have a positive discriminant in both cases. So it's really just going to come down to my second order partial with respect to x and whether it's positive or negative. So I extend upon this and I evaluate my second order partial for 0, 0. Oh, we already did 0, 0, sorry. That's the saddle point. And I wrote 0, 0 again like a fool. Can't get out of my own way sometimes. So that's just a 12. That's greater than 0. So we now know that at 1, 1, negative 1, what happens when my second order partial is positive? What do my conditions tell me?
Either minimum or maximum, but
It's minimum.
yeah.
Local min. All right. And then when I plug in negative 1, negative 1, I get a positive again, right? So it's still a local min. Now the diagram helps, definitely. And I pick and choose my battles when it comes to that. Sometimes I want you to have a diagram on a test to refer to, and then sometimes I don't, right? Because if the diagram gives away everything, then that's not what I want. You know, like if I'm asking you to find the volume of a sphere, but I don't want you to know it's a sphere, then I'm defeating my own purpose if I give you a nice picture of a sphere on the test, right? But in this case, I'd be more inclined to give it because once you get, first off, you can see that we have z values of 1 and negative 1. These two are at the same level, at the same z level. So what's true for one is probably true for the other. It's just a question of whether this 0, 0, 1 was a maximum or a saddle point, all right? So what's happening is, I mean, we can't see up in the nether regions there, but if we could, we would see that this point has values of z that are both higher than it and lower than it. All right, so there's a transition that does not allow for it to be the highest point, to be the king of its particular hill. Question? They're both local mins, yeah, because we have two legs here. So this one is the local min on this side, and the other one is the local min on the other side.
The first two I parts that it's asking us to take this find local min and max. It's asking us to do it with f of the double derivative of x. Would we do that for y as well? If it didn't happen that our x to the power 4 is also our y to the power 4.
For which part?
See how we find our local min and max? We
The
plug it into
rules,
these
number
x,
1 and 2.
x.
Oh, you're talking about these bad
What
boys.
we do with y?
We don't bother with the
The
second order partial with respect to y.
Okay.
Yeah. We only look at it with respect to x. All right, so I'll put a star on number 7. That's actually a pretty tricky one. It does, I guess it doesn't have to be, but it requires a different way of thinking about it. So if you struggle with that one, I understand. I'll definitely take some time and go over that on Thursday. That's what I'll do. So shortest distance to the plane requires you to use the distance formula. Now it's 3 variables, so we're talking x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared plus z sub 2 minus z sub 1 squared. All right. So we have our plane of x plus 2y plus z equals 4 and our coordinate. All right. So what we have to do is define this in such a way that we're finding the distance between any point on the plane and that particular coordinate. So what we'll do is we'll call a point on the plane, any point that we want, it doesn't really matter. We're going to call that point x, y, z. All right? We're going to call it that because that's what it is. All right? So what I would say is x minus 1 squared plus y minus 0 squared plus z plus 2 squared. All right, and so what we want to do here is use our knowledge of partial derivatives to figure out what the minimum distance would be between these 2 points. All right, so that understood point that's on the plane, x, y, z, that we really haven't defined yet, and that point in space. Now, we learned a technique in the last unit using vector relationships to help us find the distance. It involved projections and things like that. But what we're going to do is use the second derivative test as an alternative method. But if you really think about it, just going back to the last example, we were working with a function of x, a function in terms of x and y, not a function in terms of x, y, and z. So we have to make an adjustment. The good news is we have a relationship between x, y, and z. X plus 2y plus z is equal to 4, which means that z is equal to 4 minus x minus 2y. So I could redefine my function as x minus 1 squared plus, I'll clean the middle part up to y squared, which I think is a reasonable thing to do. And then I'm going to replace the z here with what z is equal to. And this ties back into the last unit in a nice way, because when we were finding the distance between planes, we had a point in space, and I said that you needed to come up with a point that's on the plane. And the way that we came up with a point on the plane was to determine on our own, decide. You know, you just pick. I want x to be equal to this. I want y to be equal to that. And then use the equation of the plane to determine what z has to be. Right? So you had control over x, you had control over y, but then z had to be something to satisfy the equation. And it came up on the last unit test also. That's what's happening here. I'm letting x be whatever it wants to be. Y can be whatever it wants to be, but z has to follow this relationship. Right? Whatever x and y are, they have to be plugged in here to give us a particular z. Right? So when I replace the z with 4 minus x minus 2y, I get a new quantity of 6 minus x minus 2y, quantity squared. All right, so that's my function of x comma y. All right, and that's what I mean when I say I'm going to just get you started on this, because this is what you're going to find the partials. You're going to find partial with respect to x, partial with respect to y. You'll need your second order partials and your mixed, and apply second derivative test. And once you do that, you'll come up with an ordered pair that gives you, you might come up with more than one critical value. That's the thing to keep in mind. If you do, you need to flesh out which ones give you the minimum and which ones give you the maximum. Now, it wouldn't necessarily, I don't think anyway, make sense for this to return a maximum, because if it did, I mean, you're really thinking about a line going from a point in space to any point along a plane. There would be no maximum, because the highest would be an infinite distance. All right, but the shortest should be the straight line distance, the orthogonal vector between the plane and the point in space. All right, so you got your work cut out for you, but like I said, we'll start off next class with the continuation on this problem. All right.